Hello everyone, I'm Angelo D'Ambrosio, medical doctor and specialist in public health. Actually, at the moment, undergoing a PhD in infectious disease modeling at the Freiburg University. As you know, this is going to be a small course about infectious disease modeling. We will go through the very basics of this very complex topic and trying to describe what does this mean to model, how to draw insights from these models, how to build them if you are curious in the more technical aspects. So let's start. A small outline to begin. We will see an overview of so-called compartmental models, which are the most common models for infectious disease modeling. We also will see some extensions. I will show you how to draw some epidemiological insights from these models. And if you're interested, we will also see some practical examples using R, which is a common statistical software environment to build infectious disease models. Some resources. I found very useful the book of Winicky and White, called Infectious Disease Modeling. This is very good for beginners. They go very slowly through the math. They don't give almost anything for granted, and they never go too much into the complexities of these models. But if you want to step up, then there is the book from Keeling and Rouhani, which is a little bit more advanced. And if you're interested more in the practical aspects, then there is the book from Bjornstad, which is called Epidemics, which is about the actual building of these models using R. So what does it mean to model and why is it important? Models are so-called useful simplification of reality. I like to quote the sentence from George Box, a famous statistician. He used to say that all models are wrong, but some are useful. What does it mean? It's very hard to create realistic models of complex phenomena, and infectious disease, but also social phenomena or medicine are very complicated to describe precisely. So what can we do? We just try to create models which retain the most important aspect of reality for our interests, and removing all the stuff that doesn't make much of an impact in the phenomena that we are going to study. Modeling is very useful to understand the phenomena, to decompose the phenomena in their components, and especially to make predictions. It is said that models are good only as the prediction they make. If you create a model and then the models create predictions that are totally different from the data you're trying to model, then it means that some big assumption in this model is wrong. There are many ways to build models. One approach is so-called the top-down, in which you start from the data and then you add the components in order to fit the data that you're observing. This is very good when you don't have a good idea of the phenomena that you are trying to model. But the risk is that you are adding components that don't have really a causal or mechanistical interpretation in your model. And also it's very easy to so-called overfit your data, that is creating models that describe precisely the data you're observing, but they actually don't mean anything. Another approach is called bottom-up, in which you start from the domain knowledge about the phenomenon that you're trying to describe. And so you pick your components and you put them together knowing what these components are supposed to do mechanicistically, and how they're supposed to interact. And then eventually you compare your model with the real data and see how much it fits the data that you observe. This is more the approach that is more used in physics. And we are trying doing infectious disease modeling to replicate this approach. Why infectious diseases? Well, infectious diseases are a growing public health problem, as we just observed with COVID. we thought that infectious diseases was a problem of the past because due to antibiotics and public health practice, we thought that they were going to disappear from the world, but nature didn't agree with this, and recently we are seeing our new rays of infectious disease related problems, either epidemics or antibiotic resistant pathogens. So it's very important in this moment to study infectious diseases and learn how to control them. Infectious diseases are also very interesting to model because they don't have many components compared to chronic disease in which you have the genetics, the behavior, and random events that mix together in very complex way to drive your risk of heart disease or diabetes. In infectious disease, you have just one etiological agent, that is the pathogen, which then interacts with the hosts, which that is us or animals, and the environment. So it's relatively simpler to model more complex, to model infectious diseases in a more complex way. But again, this is not as simple as it may look, and if you want to go into more details, then you discover a lot of hidden complexity due to the relationship between the pathogen and the host and the environment. We will see how it is possible to get a grasp of this complexity as we make our model more and more advanced. There are many kind of models for infectious diseases. We can start from the more complex, which are called agent-based models, in which you follow individual agents through time. And these agents can be the pathogen, can be the host, can be, for example, pathogen interacting with even cells into the host. They can be exponentially complex. They require a lot of computational power to be run, but they are extremely powerful. Then there are the so-called compartmental models, which are the focus of this course, which are much more simplified. You divide your population into compartments defined by certain characteristics, and then you just model how the people move from one compartment to the other. In the middle of these two realities, we have the so-called network models, in which you have still individual agents, but they don't have complex behavior. They don't interact between themselves in complex way. You just model the kind of contacts that these agents have one with each other. Another kind of model that more or less join all of them is the so-called metapopulation model, in which you can have models of different times that work together to covering different aspects of the phenomenon. For example, it's very common to use metapopulation models for disease that moves between cities. So you can have a compartmental model inside a city, and then you can use a network model to study how the people move from one city to the other. For example, this kind of models is very used for influenza, to study how influenza move throughout the world using people on airplanes. So you can have a compartmental model in a certain region of the world, and then you have a network model that study how the people move from one part of the world to the other. Okay, in the next slides I will go into the details about compartmental models.